Hello everyone, welcome back to the online lecture series of fluid mechanics. We were discussing the hydrostatic pressure distribution, and in the last lecture we have derived the fundamental equation of hydrostatics. So according to the fundamental equation of hydrostatics, the fundamental equation of hydrostatics, what we got that the negative gradient of P plus rho G is equal to 0. Now, this can also be written as the gradient of P is equal to rho G. Here, this is the gradient operator, and this represents the spatial rate of change of any property, which in this case is pressure. So, this is the gradient operator. This is nothing but the spatial rate of change of any property. So this can be written as del upon del x I cap, del upon del y j cap, plus del upon del z k cap. Now using this, we can now write down the same thing as del p upon del x I cap plus del p upon del y j cap plus del p upon del z k cap will be equal to, now because here actually g is the acceleration due to gravity vector, and so if we write down the gravity g can be written as, since g is a vector, so any vector can be written as the magnitude of the vector into the unit vector along which the vector is acting, which in this case is the downward direction. So here we will write negative of k cap. So instead of g vector, we can now write down minus g k cap, where g represents the magnitude of the acceleration due to gravity. So now we can write down as rho g, taking the negative sign here, for k cap. Now this equation can also be written in component form. If we see both the sides of the equation, we can find out that whereas in the left hand side we have terms containing the I unit vector, j unit vector, but there are no such terms in the right hand side. So there are no terms containing the I unit vector on the right hand side and j unit vector on the right hand side. We only have the terms containing the k unit vector. So which implies that del p upon del x is equal to 0, and del p upon del y is also equal to 0, and third, del p upon del z can be written as minus of rho g. So we have del p upon del z is equal to minus of rho g. Now, since del P upon del x is equal to 0, del P upon del y is equal to 0, which means that P is independent of the x and y axis. It is independent of x and y axis, in which case we can now replace del P upon del z by simply dP upon dz, and this dP upon dz will be equal to minus of rho g. So this is the second form of solution which you have got. Now from here we can also write down that dP can be written as dP is equal to minus of rho g dz. Now you can say that this is actually the solution of the hydrostatic equation which we have got. Solution of the hydrostatic equation, or the fundamental equation of hydrostatics. Now, using this equation, we can calculate the pressure at two given points, say point 1 and point 2, simply by integrating it between the 2 points. So, this can be written as integration of dP between the 2 points will be equal to integrating the terms in the right hand side, which is minus of rho g dz. Now, we will apply this for both cases, which are first will be for incompressible fluids and second we will apply it for compressible fluids. So let's apply it for compressible fluids first. Now for compressible fluids, what do we mean by, first let us apply this for incompressible fluids. So for incompressible fluids, we mean for liquids and for such gas flow situations where the variation of density, in which the variation of density can be ignored. So in that case, the variation of pressure can simply be calculated by using this equation. So let's do it. So first, for incompressible fluids, mainly for liquids. Here we will consider say a static fluid, and we take a reference axis like this. Suppose this is the z-axis, let this be the y-axis, and let this be the x-axis. Here, this is the free surface of the fluid, and we will consider 2 points, or say point 1 and point 2, such that the elevation from this reference axis be indicated as, suppose for 1 it is z1 and for 2 let it be z2. So the difference between the elevations 1 and 2 will be equal to z1 minus z2, which let us assume that it is indicated as h. Now here, by using this equation, we have integration of dP is equal to integration of minus of rho g dz. Now, in case of liquids are those substances for which we assume that the density is constant. So we can take out the constant terms and the remaining will be in the integration. So we have integration of dP. If we integrate it between the 2 points, say 1 and 2, 1 and 2, we will get P2 minus P1 will be equal to, taking the constant terms outside, we have minus of rho g, and integrating dz, we will get z2 minus z1. Or we can also say that P2 minus P1 will be equal to rho g z1 minus z2. Now the term z1 minus z2 has already been indicated by using the letter h. So we can now rewrite it as P2 minus P1 is equal to rho g h. So we can calculate the pressure at any point P2 will be equal to P1 plus rho g h, or in a more general form, we can also say that since this point P2 is a below point and then the point 1, so in a more general form, we can say that P below is equal to P above plus rho g h. So this is a very important conclusion which we have got, that the pressure at any point below will be equal to pressure at the point which is above plus rho gh, where h is the difference of elevation between the 2 points. Now suppose we say that this is the free surface of the fluid, and since this is the free surface, the pressure that will be acting here will be P atmospheric. Now let us consider one more point, say any point, say M, such that the depth of this point M from the free surface, let it be H. So we have the depth of the point M with respect to the free surface, it is H. Now we can use this equation and find out the absolute pressure at the point M. So what will be the absolute pressure at point M? Pm absolute will be equal to the point above this point M is the free surface where the pressure is P atmospheric. So we can write P atmospheric plus rho G H. This is given by using this equation. P below is P above plus rho GH. The below point is this point which is M. So this is Pm absolute is equal to P atmospheric, which is the pressure at the point above this point M, or the free surface PATM plus rho GH. From this we can now calculate the gauge pressure at M. So the gauge pressure at M can be given as P gauge will be equal to Pm absolute minus P atmospheric, which is equal to rho GH, or P gauge is equal to rho GH. Now what does this implies? This simply implies that the pressure at any point in an expanse of a stagnant fluid with a free surface exceeds that of local atmospheric pressure by an amount equal to rho GH, where H is the depression or the vertical depth of the point from the free surface. So let me write down. So we got P gauge is equal to rho GH. Now this implies that the pressure, you can write down the pressure at any point, the pressure at any point in a stagnant fluid, in a stagnant fluid with a free surface exceeds the local atmospheric pressure, exceeds the local atmospheric pressure by an amount rho GH. So at any point in a stagnant fluid with a free surface, the pressure exceeds the local atmospheric pressure by the amount rho GH, where H is the depression or the vertical depth of the point from the free surface. So here, where H is the depression or the vertical depth, depression or vertical depth of the point from the free surface. So likewise, we can also calculate the gauge pressure at various points in the vertical depth of a fluid. Now, the linear variation of pressure with depth below the free surface is what is known as the hydrostatic pressure distribution. Now, the variation of the gauge pressure in a liquid below the free surface can be illustrated as, suppose this is the free surface and we take various points. The free surface is indicated by using this. Now we take various points, say we have point 1, let this be point 1, which is at a vertical depth of h1. Let us say that this is point 2 and this is at a vertical depth of h2, and let this be the bottom. So here the pressure that is acting at the free surface, it is P atmospheric, and so here there will be a zero gauge pressure. Now the pressures can be represented as, at the point 1, which is at a vertical depth of h1, the gauge pressure that will be acting will be rho g h1. Similarly, at point 2, which is at a depth below than the point 1, we will have rho g h2. And if the overall depth of the fluid, if it is h, so at the bottom surface, there will be a gauge pressure which will be equal to rho g h. So here we get a pressure triangle, and this represents the gauge pressure at various points in the vertical depth or depression of the fluid from the free surface. Now let's calculate the same, the variation of depth for compressible fluids. In case of compressible fluids, we know that the density changes with change in pressure and temperature. And by compressible fluids, we mainly talk about the gases. So we have an ideal gas equation, which is P is equal to rho RT. So let us now write down for compressible. So we have, for compressible fluids, we take the perfect gas equation or the ideal gas equation. Ideal gas equation, which is P is equal to rho RT, and here density can be calculated as P upon RT. Now, depending upon the process which is involved, the process may be isothermal process or adiabatic process, or we can say that if there is no friction or no heat transfer, we can also say that the process is isentropic. We can analyze, we can calculate the variation of pressure according to the various process which is involved. So first let us try to see if the process involved is an isothermal process. Now, what is an isothermal process? A process which is carried out at constant temperature. So here we have T is equal to T naught, which is constant. So we have dP according to the equation which you have already got. dP is equal to minus of rho g dz. Now this dP upon dz can now be calculated as dP upon dz will be equal to minus of rho g, or substituting the value of density from here, we can write down minus of P upon RT to G. Now on rearranging, we get dP upon P can now be written as minus of G upon R dz upon T. Now, here since the process is an isothermal process, the temperature is also constant. So we can write down upon integrating, suppose we integrate this, we have integration of dP upon P will give ln P2 upon P1. This will be equal to minus of G upon R T naught, because temperature is constant, Z2 minus Z1. So you can say that ln P2 upon P1 is equal to minus of G R T naught Z2 minus Z1, and removing this log, we can write down P2 upon P1 is equal to exponential of minus G R T naught Z2 minus Z1, or you can also remove the negative sign and write down Z1 minus Z2. So this is the expression which we have got. So from here we can also write down that P2 can be written as P1 exponential term is minus G Z2 minus Z1 upon R T naught. So this is the variation of pressure for a compressible fluid or for a gas in case when the process is an isothermal process. Now let's discuss the variation of pressure for non-isothermal fluids. Now here, as you can see, I have already drawn the diagram. Diagram is actually, this shows the variation of temperature in the different spheres of the atmosphere, and it can be seen here that in the first sphere, or we can say that up to a certain altitude, say around 10 kilometers, the temperature is decreasing linearly. Then in the second sphere it is constant, and then it is increasing, and again constant, it is decreasing, and again constant. So this is the variation of temperature in the different levels of the atmosphere. And here we see that the temperature can be seen to decrease linearly up to a certain altitude, say Z, and that variation of temperature can be written in the form of an equation, which is T is equal to P naught minus alpha Z. Now, in this equation, T naught represents the temperature at the sea level, or the absolute temperature at the sea level. T naught is the absolute temperature at sea level, and Z and alpha is actually a constant which is known as lapse rate. Lapse rate, and it is expressed in Kelvin per kilometer. And for standard atmosphere, we have the value of alpha. It is around 6.5 Kelvin per kilometer. And for T naught, we have around 288 Kelvin. Now, this equation of P can be used in the in the equation of the pressure variation, which we have already derived. So, the equation which we have derived was, uh, we have already derived the equation dP upon P is equal to minus G upon R dZ upon T. Now, instead of T, we will write down T naught minus alpha Z, and the pressure between 2 points can be easily calculated by integrating this equation. So let us integrate it. So we will integrate it. On integration, we will get ln P upon P naught will be equal to minus G upon R alpha ln T naught minus alpha Z upon T naught. So We can also write it down in terms of P. We will write down P upon P naught. P upon P naught can now be written as this term 1 minus alpha Z upon T naught, and in the exponent there will be minus G upon R alpha. So this is the final equation which we have got here. P naught is actually the pressure at altitude Z, which is measured from the sea level. So P naught represents the pressure at altitude Z measured from sea level. So in case of non-isothermal fluids, the variation of pressure can be written in the form of this equation. Here we have got one constant which is known as the lapse rate, and it is denoted in terms of Kelvin per kilometer, and it is attributed to the fact that the temperature, actually it can be seen that the temperature is decreasing linearly up to a certain altitude, and thereafter it shows certain pattern. It is constant in the stratosphere level, then it again increases, then remains constant at certain altitude, then it again goes on decreasing, then again it remains constant, and then it again increases. So we are more concerned about a certain level, that is the troposphere, and in the troposphere the variation of temperature can be expressed in terms of this equation. We will use this equation for T and find out the equation for P upon P naught, where P naught is the pressure at altitude Z, which is measured from the sea level. So this is how the pressure is measured from for two different conditions, for isothermal condition and for the non-isothermal conditions. Next, we will see a new topic in our next lecture. Thank you.